Hello friends, welcome to my YouTube channel. So last time we did the multiple choice questions from TIFR GS 2026. So today we will do part B, the true false part. So let us start. Let f from R to R be a continuously differentiable function and S belongs to R be a bounded subset. Then there exists a constant strictly greater than 0 such that fx minus fy is less than or equal to this for all x comma y belongs to S. So let us just see. So continuously differentiable means f prime of x is continuous, right? Now we can restrict f prime in minus m comma m to R. What is m? So as f is bounded, then it is true that for all x belongs to S, mod of x is less than or equal to m, right? Or strictly less than m. There exists some positive real number, right? Because this is bounded. Now what we will do that we use mean value theorem. So by mean value theorem we have fx minus f of y is equal to f prime of c x comma y times mod x minus y, where x comma y belongs to minus m comma r, m comma m, and cx comma y is inside x comma y. Okay, so if x comma y belongs to minus m comma m, c of x comma y is also belongs to minus m comma m, right? Now if you take x comma y belongs to S, this will not change this thing, right? Because if x comma y belongs to S, then c x comma y is belongs to minus m comma m. Now the point is, we know that as f prime is continuous, because this is continuously differentiable, if f prime is continuous and we restrict f prime on minus m comma n, this is a bounded closed interval. So on bounded closed intervals any continuous function is bounded, right? So we can say that f prime of z is strictly less than b for all z inside minus m comma m, right? So as cx comma y is inside minus m comma n, we can say that f of x minus f of y is less than or equal to b times x minus y for all x comma y belongs to S. So this is true. Okay. So there exists there exists a continuous bijection from Q to 0 1 to 1 to 2026. Okay. Okay, yeah, so let us just do it here. So we have to we have to produce a continuous surjection from Q to 0 1 to 2026. So Q to 0 1 to ... 2026. So how many elements are there? So there are 2027 elements, right? So we know if we pick 3 points, this will divide R into 4 regions, right? So if you pick n number of points, this will divide R into n plus 1 regions, n plus 1 segments, correct? Because 1 point divide into 2 parts, 2 points divide into 3 parts, so in this way. So now so if you choose, let us choose 2028 irrational numbers. Increasing in increasing order. Okay, no, sorry. So we have to choose, there are how many elements? Okay, so we want how many regions? We want 2027 regions, so we have to choose 2026 irrational numbers. Okay, so yeah, you can define it like that. So we know square root of any prime number is irrational, right? Square root of any prime is irrational. Just choose square root of consecutive 2026 prime numbers. That's it. So then define the function from Q to this set 1 to 26 as follows. F of R equal to 0 1 2 dot 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 2026. Okay, how you can define that? Yeah, so R is belongs to Q. R is from rational number. So if R is less than root over this 1, if R is strictly greater than P2 and strictly less than P1. So see that R will not take the values root over P1, root over P2, because R is rational and we know these numbers are irrational. Okay, so yeah, in this way you can construct P3 and P2 and continue in this process and get root over R is less than sorry, I have to put P1 here, P1, P2, P2, P3. Yeah, sorry. So R has to be inside P2 and P3. So yeah, so this is the definition. If so this is the definition, and these functions are continuous, right? So the idea is that you divide, you select some irrational numbers and you divide constant on this region. So let's say this is P1, root over P1, this is root over P2, root over P 2025, and this is root over P 2026. So just define constants over the rational numbers on this guy, constant 0, and over the rational numbers over this region define 1, over the rational number of this region define 2, and so on, right? So then in this way you can define a continuous function. So yeah, this is perfectly surjective, right? This is surjective. So yeah, so this is true. Okay, the subset X such that a continuous function on 0, R, 0, 1 to R such that mod of fx minus fy is less than equal to x minus y power half for all x, y belongs to 0, 1. Okay, of this is this subset is compact or not. Okay, so we are working with sup norm, right? So what is the norm? Norm is just supremum of x belongs to 0, 1 f of x, right? So this is the norm. Okay, so now you have to see this this set is compact or not. So under this supremum norm, a necessary condition for compactness we need this is necessary. We need that The set has to be bounded. If this is compact, then X has to be bounded. Okay. So let us see. Let us define a function. So let us define a function 0, 1 to r. So define it f of c of x equal to c for all x belongs to 0, 1. So you can make c large as much as you possible, as much as you want, right? Then it's clearly satisfied because the constant function clearly satisfies this, because if fc minus f of y is just 0, right? So it's clearly satisfy the condition given in the question. But the point is the set is not bounded, because you can make c as large as you want, right? So x is not compact. Okay, so this is false. Okay, so there is no continuous bijection from R to 0, 1. So this is very easy problem, because if there exists any bijection from R to 0, 1, so we know that a continuous bijection from R to 0, 1 closed interval 0, 1 has to be monotone, right? Why? So I think most of us know this theorem. So let us just quickly recall why this is the case. Because if this is continuous bijection, then let us choose 3 points x, y and z in increasing order. Let us choose 3 points. So if fx is less than f of y, strictly less than, so there has to be strictly less than, right? Because we assume this is a bijection, so this has to be injective. And let's say f of y is strictly greater than f of z. So we want to show that f is strictly increasing. So if for a point this will happen, then we will show that f is strictly increasing. So you can show that f is strictly decreasing by taking 1 minus of f, right? So just shift it at 1 minus of f if decreasing at one point, decreasing for x comma y, any x comma y belongs to R. Okay. Okay. Right. So why this is true? Let us say if f of x is less than f of y and f of y is greater than f of z. So let us draw the picture. So here is x, here is y, and here is z. So let's say the graph is this. Okay. So this is f of y, this is f of x, and this is f of z. So you see, here we assume that f of z is strictly bigger than f of x. Okay. So let us draw this. Draw the line. So there is some subtle here. So let us just draw the line. So this is the line. So this is f of z. So now see that f of y is greater than, f of y is strictly bigger than, so f of y is bigger than f of z. And here we assume that f of z is strictly bigger than f of x. So what we have? So f of z is inside f of y and f of x. So there exists a cz inside x comma y such that f of cz equal to f of z, right? This is true. Okay. So then what you have? Then we can have a contradiction, right? Because cz is inside x comma y, but what we have? So cz equal to f of cz equal to f of z will imply z equal to cz. CZ is inside x comma y. That is not possible because z is strictly bigger than y, right? So that is not possible. Yeah, so you can pick an element from that. By intermediate value theorem you can get a pre-image of this point, and at the same height you can have another f of let's say, okay, so let's say this height is f of this height is, let's say this height is h and this height is also h. Then you can have a point inside that c1 and you have a point inside c2 such that f of c1 equal to f of c2 equal to h. This implies c1 equal to c2. That will not be the case, right? Okay, so f has to be strictly monotone, right? So if monotone increasing, then f is let's say f is monotone increasing, then r from 0 comma 1 to 1 you have a c such that f of c equal to 1. So then if we want to find that f of c plus 1 equal to so as this is if it is, first of all, let's say this is strictly increasing. If it is strictly increasing, then f of c1 ac plus 1 has to be strictly greater than f of c. That's not possible. Let us say that it is strictly decreasing. So then there exists a point b such that f of b is 0. Now choose f of b plus 1. So as it is strictly decreasing, then f of b plus 1 is has to be less than f of b. Again, not possible, because the image set is inside, because the image of f equal to 0 comma 1. So that's the proof. Yeah, okay, so this is true. Let A and B, A comma B be a linear endomorphism of a finite dimensional vector space over a field. If A and B are diagonalizable, then AB is diagonalizable. Okay, so let A equal to 1 0 0 minus 1 and B equal to 0 1 1 0. Then okay, then what is the characteristic polynomial of that? So 1 minus x 0 0 minus 1 minus x. If you want to find the determinant of that, this will give you x plus 1 times x minus 1. So this is diagonalizable because the minimal polynomial is the minimal polynomial is that. So, and minimal polynomial has distinct roots, distinct factors. So A is diagonalizable. Similarly, for B, if you find the determinant of B minus x I2, this will give you minus x 1 1 minus x, which is x square minus 1, which is x minus 1 x plus 1. Yep, same thing. So again, this is diagonalizable because the minimal polynomial is minimal polynomial divides this x minus 1 times x plus 1, and in this case the minimal polynomial is exactly x minus 1 times x plus 1, and this has distinct factors. So B is also diagonalizable. So these are diagonalizable. But if you compute A times B, so these are endomorphism over R. So we are considering M2 R. Okay, so then AB equal to 1 0 0 minus 1 and 0 1 1 0. Okay, this will give you 0 1 minus 1 0, right? But what is the characteristic polynomial of that? That is minus x 1 minus 1 minus x. The determinant will give you x square plus 1, and this is not factorizable over R. So it is not diagonalizable. Not diagonalizable. Right? Okay, so this is false. Okay, so if A belongs to GL5C and A square is diagonalizable, then A is diagonalizable. Okay. So, okay, so let us do it here. Oops. So, A square is diagonalizable and A is inside GL5C, right? So A inside GL5C means determinant of A is non-zero. Okay. So that means 0 is not an eigenvalue. Eigenvalue of A. So yeah, if 0 is not an eigenvalue of A, that determinant is non-zero. Non-zero imply determinant of A square is non-zero. So 0 is not an eigenvalue of A square also. Now, so it is diagonalizable. We know a matrix is diagonalizable over a field if and only if the minimal polynomial, its minimal polynomial of A square is can be written as product of some distinct linear factors. Distinct means alpha I is not equal to alpha j for I not equal to j. Okay. Now the minimal polynomial A square is this. So that means okay. So that what that means? That means A square minus alpha 1 dot A square minus alpha k is 0. So that will imply A satisfies x square minus alpha 1 dot x square minus alpha k. You can factor this as x minus root alpha 1 times x plus root alpha 1 dot x minus root alpha k times x plus root alpha k. So now look that if you look at any plus minus alpha I is not equal to any plus minus root over alpha j. Why? For I not equal to j, because if you square both sides, so let us assume that plus minus alpha equal to plus minus root alpha j. If you square both sides, you will get alpha equal to alpha j. That is not possible. So we have this, and we know this is not equal to minus root over alpha I, because alpha is non-zero. Why? Because look at this A is not equal to A belongs to GL5C. What that means? That means determinant of A is non-zero. Determinant of A square is non-zero. So 0 is not an eigenvalue of A square, right? And we know that A square and the characteristic polynomial. So the characteristic polynomial of A square and the minimal polynomial of A square has same roots except multiplicities, right? So the characteristic polynomial of A square does not contain 0 as its roots, 0 as a root. So then a minimal polynomial of A square does not contain 0 as a root, right? So that implies alpha is not equal to 0. You can do it otherwise. So you can do it by this method, that minimal polynomial of a matrix, let's say M, divide characteristic polynomial of a matrix, right? If the determinant is non-zero, so what does that means? That characteristic polynomial, so characteristic polynomial of A is just minimal polynomial of M times some other polynomial, let's say gx, right? So if the minimal polynomial has a 0, let's say x divide the minimal polynomial. So let's say 0 is a root of this minimal polynomial. Let's say characteristic polynomial is f of x and minimal polynomial is h of x, right? So let us just put f of 0 equal to h of 0 times g of 0. So h of 0 is 0 if minimal polynomial has a root has 0 as a root, but f of 0 is just plus minus determinant of m, right? So that is not possible here. So so the minimal so alpha I is a non-zero, so that will imply that a satisfies this, right? It satisfies this product over I x minus root alpha I times x plus root alpha I. So this polynomial has all distinct linear factors. Now the minimal polynomial of a divides this polynomial, let us define this is p of x, divides p of x. As p of x has distinct linear factors, the minimal polynomial of a also has distinct linear factors. Okay, so that means that will imply a is diagonalizable. Okay, so so this is not done. This is true. Okay, right. So now let's say a function from R to R is said to be periodic if there exists a positive real number c such that f of x plus c equal to fx for all x belongs to R, then the set of all periodic function is a linear subspace of real vector space of all functions from R to R. Okay. Set of all periodic function is a linear subspace of the real vector space of all functions from R to R. Okay. Right. So let us define fx to be 0 when x is inside z and 1 when x is not inside z, and g of x to be 0 when x is inside root 2z and 1 when x is not inside root 2z. Okay, and then we have to show that f is periodic. So let us compute f of x plus 1. So if x is inside z, then x plus 1 is inside z, right? So this will be 0. So f of x and f of x plus 1 when x is not inside z. So if x is not inside z, then x plus 1 is not inside z also, right? So that will imply this value is 1. This is also f of x, right? So f is periodic with period 1. Let us compute g of x plus 1 when x is inside g of x plus root 2 when x is inside root 2z. So if x is inside root 2z, then x plus root 2 is inside root 2z, right? So then it is 0, then is g of x. And if let us compute x plus root 2 when x is not inside root 2z. So if x is not inside root 2z, then x plus root 2 is not inside root 2z. So this the value is 1, so which is g of x. So it is periodic, has period root 2. So now let us just compute f of x plus g of x. Okay, so for a linear subspace we want that if f and g are periodic functions, then that their addition is also a periodic function. So let's say it has period c for positive c. Okay, for positive c for all x belongs to R. Okay, now put x equal to 0, we have f of 0 plus g of 0 equal to f of c plus g of c. Okay. Now now what is the value of f of 0? So f of 0 is 0, g of 0 is 0, right? So this is 0. So f of c plus g of c is 0. Okay. So now look at that, the f of x is greater than equal to 0 always, and g of x is also greater than equal to 0 always. So these are positive functions, and their sum is 0, implies f of c equal to 0 and g of c equal to 0. So f of c equal to 0 means c is inside. So f of c equal to 0 implies c is inside z, and g of c equal to 0 implies c is inside root 2z. Okay. So that means c is some integer m and equal to root 2 times n. Okay. So then what will be the possibility? Okay, so m equal to root 2n. So if n is non-zero, then we can write root 2 as m by n, right? But root 2 is irrational, m by n is rational, so that's not possible. So that will imply n equal to 0 equal to m is also 0, and m equal to c we know, right? So c has to be 0, but for periodicity we need c is strictly bigger than 0. That's not possible. So fx plus gx is not periodic, so this is false. Okay, so px belongs to cx is a polynomial which is not equal to x, then the polynomial px minus x divides the polynomial p of px minus px. Okay, so let's say p of x is a polynomial inside c of x. So let's say p of x equal to an x power n plus an minus 1 x power n minus 1 plus dot 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 right, dot 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 a naught. Now so we know that px minus py, we can write it as x minus y times some polynomial in xy, right? Some two variable polynomial in xy, right? Because px is this ak x to the power k from 0 to n. Now px minus py is what? Px minus py is summation ak x to the power k minus y to the power k. Now just pull out one factor of x minus y here, so we will get this, right? This is easy, so we can write it like that. Okay, now just put y equal to px here in this equation. So we have px minus p of px equal to x minus px, p of x, times c of some polynomial in this. So yeah, now c is a two variable polynomial. If you replace y by px, then you can change the whole thing is inside cx, right? So you can write it x minus px times some hx, where hx is inside cx. Okay, now p of px minus x is equal to p of px minus px plus px minus x. Okay, so you can write it as px minus x by this equation, px minus x times hx plus px minus x. Okay. Yeah, so which is equal to px minus x times h of x plus 1. So that means px minus x divides p of px minus x. Yeah, so this is true. It's true. Let A be a square matrix with non-negative real entries such that the sum of the entries of each row is 1. Then each eigenvalue of A has absolute value less than or equal to 1. Okay. So, A be a matrix Aij m cross n. Sorry, a square matrix. Oh, sorry. These are square matrix. N cross n. Okay. More precisely, a11, a12, and dot a1n, a21, a22. Okay. Now, okay. So let's say lambda is an eigenvalue. So that means there exists a non-zero vector c1 up to cn such that this is equal to lambda times c1 up to c. Okay. Now, what we have is that summation say j from 1 to n cj is equal to lambda ci, right? Am I correct? Yes. Yeah, just do the second I equal to, yeah, so this is lambda ci. Okay, right? So define mod c max equal to maximum of mod c1 mod c2 dot mod cn. So the maximum will be a strictly positive number because this for being an eigenvalue, this vector has to be non-zero, right? So at least one of the entries is non-zero. So mod c is the maximum of those. So and all the entries are non-zero. So sorry, all the entries are non-negative. So aij has to be greater than equal to 0. Okay. Now from this equation we have mod lambda mod ci is less than equal to summation j from 1 to n aij mod of cij, right? Which is less than equal to, you can just pick the maximum. So it is less than equal to j from 1 to n aij sum times c max. Okay, and sum of each row by the given condition. So these are rows, sum of each row is 1. So what we have, this ci is less than equal to c maximum. Okay, now we know this maximum. So mod c max equal to mod ck for some k, right, inside 1 and n. So this is the general theorem, but if you put I equal to k in this, you will get lambda k times mod ck is less than equal to mod ck, which is equal to mod c max. And as this is maximum, so this c max has to be non-zero, right? Then you have mod lambda is less than equal to 1. So the absolute value has to be less than equal to 1. So yeah, so this is true. So let X be a metric space having exactly 4 points. Then for a positive integer n, there exists a distance preserving map X from R to n, where R power n is equal to its Euclidean matrix. So I will do this by geometry. You can just check it by hand. So this is not true because yeah. So let us just define a metric X from X to R power n, that 4 points. X is a 4-point space, right? So I will define it like that. 2 1 yeah, let me think. 2 1, so it's a P Q R S and 2.21 and this to be 2, this to be 1, and this to be 1. Okay. Okay, so let us define a 4-point space ABCD. ABCD is treated as BCD. So let us define the metric first. A comma B is 1 equal to DB comma C equal to DC comma D. Okay, these are all 1. A B B C C D. A comma C has to be 2. D of A comma C has to be 2. D of B comma D has to be 2. But D of A comma D has to be, so these are the whole point, because there will be 6 possibility. 4 choose 2 is 6. We have to define 6 distances. D of A comma D is 1. Okay. Now you can define it 2 or 1 maybe, but this doesn't matter actually. So this defines a metric space. Why? Because why from any element, let's say A comma C, why does it satisfy A comma some element plus A comma some another element, let's say D? Why does it satisfy? Because so let us do a general thing, right? So if in a metric space D of X comma Y is inside this two set 1 comma 2, then this trivially satisfies the metric space condition, right? The triangle inequality. Why? Because D of X comma Y, so if this is true for all X comma Y belongs to the metric space, then why this is true, that this is less than equal to D of X comma Z Z comma Y. So if this is 1, then D of X comma Z is either inside 1 comma 2 and 1 comma 2, right? This belongs to 1 comma 2 and 1 comma 2. If you add it up, so this clearly this is because D of X comma Z plus D of Z comma Y is inside 2, 3, 4, right? So D of X comma Z plus D of X comma Y is inside 2, 3 and 4. Clear? So that's why is greater than equal to 2. Yeah, so which is greater than equal to d of x comma y. So that's the reason. Okay, so this trivially satisfy the condition. So let's say under this condition we have a map from x to Rn, the distance preserving map. So a, let's say a maps to P, B maps to Q, C maps to R, D maps to S. So f of A, f of B, f of C, f of D. Okay, so that 4 points inside the metric space, inside Rn, sorry. So distance between okay, so what we say that, let's say, yeah, so if you look at the norm of f of a minus, so let us do it formally, you can check it by hand. So it is less than equal to the norm of f of a minus f of b plus f of b minus f of c. Okay, so the equality holds when because if you add those two vectors, so this is a, if you read the linear algebra chapter, inner product space or non-linear space, then you will see this type of inequality. This is called Cauchy inequality. So if you add these two vectors alpha beta, then you will get this vector, and norm of alpha plus beta is less than equal to norm of alpha plus norm of beta. Now the point is that the equality holds when alpha comma beta is linearly dependent. So f of a, so treat this f of a as a vector in Rn, right? Treat these guys as a vector in Rn. So f of a minus f of b and f of b minus f of c are linearly independent. Sorry, linearly dependent. Okay. Okay. So in geometrically it says that f of b lies inside the line joining f of a and f of c, and as this map is distance preserving, so the distance between f of a and f of b is 1, and distance between f of b and f of c is 1, and distance between f of a and f of c is 2, right? So that means f of b is basically f of a plus f of c divided by 2, or f of b minus f of a equal to f of c minus f of b. Okay, or otherwise, yeah. Okay, now similarly, so I'm defining all those. Yeah, correct. Yeah. Yeah. Similarly for f of b, f of c, and f of d. Okay, so what we defined, that f of b and f of d has distance 2, and f of c and f of b has distance 1. So c lands in the middle point on the line joining. So first of all, f of c is inside the line joining between f of b and f of d, right? So that means similarly f of c equal to f of b plus f of d divided by 2. This will imply that f of c minus f of b equal to f of d minus f of c. Simple, as a vector. Yeah. Now what can you say? Correct. Now So now they are so what that means geometrically, this P, Q, R are on the same line, and Q, R and S are on the same line. So this is the whole line, and this is 1 1 and 1. So f of d minus f of a is nothing but f of d minus f of ABC, C plus f of C minus f of B plus f of B minus f of A, right? So but what is f of D minus f of C? It is nothing but f of C minus f of B, right? So see, f of C minus f of B equal to f of D minus f of C, and f of C minus f of B is what? F of B minus f of A. Okay, then you can just simply say that this is equal to 3 times f of B minus f of A. Then what will be the norm? The norm means the distance, that's the Euclidean norm. This will be 3, but we are defining this norm to be 1. It's not possible, right? Not possible. Okay. It's not possible. So you can define 2 instead of 1. You can define it. Okay, so this is not true. Okay. Right. So let f from R to R be a continuous function for each positive integer n. Let fn from R to R be defined by fn of x equal to f of x to the power n. If the sequence of function fn converges uniformly on R, then f must be a constant function. Okay. So f from R to R, f from R to R be a continuous function. Okay, these are continuous functions. So f of x power n, these are also continuous function, right? And it is given that this uniformly converges to some function f of x, converges to some function g of x, maybe. Let's say g of x. Now these are continuous functions, and continuous function uniformly converges to a function g of x, and g of x then has to be continuous. Okay. Now okay, so that means fn of x minus g of x is less than epsilon for all n greater than equal to n, and for all x, so for all n greater than equal to n epsilon, and for all x inside R. This is the definition of uniform continuity, right? Okay, so g is a continuous function. So let us put f of x to the power n, because fn of x is that epsilon. Okay, now right. Okay, so okay, let's just choose x equal to 1 by 2. Let's say x equal to 1 by 2. Okay, or let us choose x is inside, x is element inside 0, 1. Okay, x element inside 0 comma 1. So this is clear that f of 0 equal to 0 from here. Sorry, f of 0 equal to g of 0 equal to f of 0 if you put x equal to 0 here, right? Now pick an element x from 0 comma 1. Then we have f of x to the power n minus g of x is less than epsilon. So as n tends to infinity, what do we have? F of x power n tends to f of 0, right? This is true. Then so we know that limit n tends to infinity f of x power n minus g of x, by definition of uniform convergent, that this is 0, right, for all x belongs to R. So if you put x equal to some number between 0 and 1, then limit n tends to infinity f of x power n minus g of x equal to 0 implies f of 0 minus g of x equal to 0. So that means g of x equal to f of 0. Okay, all right. Okay, so that means g of x equal to f of 0 for all x inside 0 open 1, but g is continuous. So that means g of 1 is also f of 0, right? Just take a sequence just tends to 1 and then apply continuity. Okay, so g is constant on so g of x equal to g of x equal to f of 0 for all x inside 0 comma 1, closed interval 0 comma 1. Now limit n tends to infinity, again we are using this f of x power n minus g of x equal to 0. Now put let's say alpha is strictly bigger than 1. Okay, let's say alpha is strictly bigger than 1. Then put, this is also true for this is for all x, right? So the point is that if you put a sequence, let's say if you put a sequence, so limit n tends to infinity x n power n, if you put a sequence instead of x, this is also 0, because by uniform convergence, by uniform convergence. Just pick the highest n, because it does not depend on what x you are choosing. Okay, now just put xn to be what? Okay, now just put xn to be alpha power 1 by n. So alpha is inside. We have to show that f is constant, right? So when alpha is inside 0 comma infinity, let's say, then limit n tends to infinity f of alpha minus g of alpha power 1 by n is also equal to 0, right? Okay, now we know that alpha power 1 by n tends to 1 as n tends to infinity, right? Okay, and then g of alpha power 1 by n tends to g of 1. Okay, so then f of alpha minus g of 1 is 0, then f of alpha equal to g of 1, that is f of 0, right? Okay, so f of alpha equal to f of 0 for all alpha inside 0 comma infinity. Okay, now You have to show for, yeah. Okay, so now put yeah, similarly we can show, yeah. So if you put x is inside minus 1 comma 0, then you will get the same conclusion, right? Because if x is inside minus 1 comma 0, then g of x has to be f of 0 then. Okay, and then g of minus 1 is also f of 0 by continuity. This is easy to prove. Okay, now pick an element. Let us just put xn to be minus alpha power 1 by n. Okay, so then limit n tends to infinity, f of minus alpha power 1 by n whole power n minus g of minus alpha power 1 by n. This has to be, the limit has to be 0, right? The limit has to be 0. Minus alpha power 1 by n tends to minus 1, right? No confusion. Then limit n tends to infinity, f of we are just taking here, so limit n tends to infinity, we can do it like that. So alpha power 1 by 2n power 2n is also possible, right? Plus 2n power 2n, because if as n the limit is 0, then as 2n is also has limit 0, this limit is also 0. So that means what we have, yeah, that will imply that f of alpha has to be g of minus 1. That is not very useful, but if we use odd, f of minus alpha power 1 by 2n plus 1 power 2n plus 1 minus g of minus alpha to the power 1 by 2n plus 1 is 0, then we know that limit n tends to infinity, f of minus of alpha minus g of minus alpha by 1 by 2n plus 1, and this guy goes to minus 1, so f of minus alpha has to be g of minus 1, and we know that g of minus 1 is what? Yeah, g of minus 1 is also f of 0. Okay, which is f of 0. So f of x equal to f of 0 for all x inside R. Okay, right. Okay, so then f is constant. Okay, so then this is true. So x comma y be finite metric spaces, then x and y are homeomorphic if and only if the real vector spaces c of x comma r and c y comma r are isomorphic. Okay, okay. As a real vector space, they are isomorphic. These are finite metric space. Okay, so these are finite metric space, that means to infinity. So these are homeomorphic, and then c x comma r and c y comma r are isomorphic. The real vector spaces are isomorphic. Okay, c, okay, these are finite metric space. Okay, c x comma r is a set of all continuous function from x to r, and x comma y is yeah, if x comma y is homeomorphic, x comma y is homeomorphic, so then there is a isomorphic as a real vector space. Okay, why this is true? Why they are isomorphic as a real vector space? Yeah, because x is homeomorphic to y, that means mod x equal to mod y. Okay, and the collection of continuous functions from x to r, so any function is continuous, right? Any function is continuous. So what are the number of functions, from x to r? It is just you can write c x comma y as a vector space, as a r vector space, is isomorphic to r x, right? You have to put the slots, that's it. And c y comma r is just isomorphic to this as a r vector space. Okay, because it is given that x comma y are finite metric spaces. Yeah, finite metric spaces. So x is homeomorphic to y, that means mod x equal to mod y, that means these are isomorphic. And if rx and ry if rx and ry are isomorphic as a r vector space, that means their dimension has to be equal, then mod x equal to mod y, and mod x equal to mod y implies x is homeomorphic to y, right? Because finite topological space, if they have finite, that means discrete topology, right? So then if you define any map between discrete topologies, finite spaces, that has to be continuous. So that means this is homeomorphism. Okay, so this is true. Suppose a finite group G is a union of its Sylow subgroups, then the order of G is a power of some prime. It is not true, right? Because if you look at S3, this has 6 elements. You can visualize it as D6. Okay, so how many elements are there? So that is R0. Okay, so you can, the elements are E, R square. Okay, and reflections F1, F2, F3. So these are the collection of rotations and these are the reflections. So 6 is 2 times 3. So these has 2 Sylow subgroups, 3 Sylow subgroups, and 1 3 Sylow subgroup. Okay, so what is the 3 Sylow subgroup? That is that's one, because this has order 3, the Sylow subgroup, and we have F1, we have F2, we have F3. Just take the union of those, you will get exactly this group, but the order 6 is not a power of some prime, so it is false. So for a 2x2 real matrix A, if the limit is existing, so we will say the limit is sin A if this limit is exist in M2R, then all eigenvalues of the limit matrix sin A have absolute value less than or equal to 1. Okay, so sin A is just limit n tends to infinity summation n from 1 to n. Okay, so n goes to infinity, n from 1 to n, minus 1 power n minus 1, a to the power 2n minus 1 divided by 2n minus 1 factorial. Okay, this is the definition. If the limit exists, you can say that. Okay, now we have to look at if some limit exists, then the eigenvalues of sin A. What are the eigenvalues of sin A? Okay, so let us just think about it. So so sin C, let's say. Okay, so let us just try once. So we know this sum n from 1 to infinity, or 1 to infinity, minus 1 n minus 1 x to the power 2n minus 1 divided by 2n minus 1 factorial. This is convergent for all x, right? This is convergent for all x. This is true. Okay, so here we will use complex numbers. So if lambda is an eigenvalue of A, then what we have, that sin lambda is an eigenvalue of sin A. Why? You can just check term wise, right? N from 1 to n, minus 1 to the power n minus 1, a to the power 2n minus 1, 2n minus 1 whole factorial. So just check sin A. So let's say it's an eigen AV equal to lambda V. So then sin A of, we have to compute sin A of V. So the point is that n from 1 to n, minus 1 whole to the power n minus 1, a to the power 2n minus 1 divided by 2n minus 1 factorial of V. So if a v equal to lambda v, then a squared v equal to lambda squared v, and so on. So a to the power 2n minus 1 v equal to lambda to the power 2n minus 1 v, right? So this will equal to summation n from 1 to n, minus 1 to the power n minus 1, lambda power 2n minus 1 divided by 2n minus 1 factorial of v. Okay, so as n tends to infinity, this is nothing but sin lambda of v. Okay, this is just a proof. Okay, so if let's say consider this matrix 1 minus 1 0 0. So this matrix has I as an eigenvalue, then sin I be an eigenvalue of sin A. Okay, now what is sin I? Sin I, by this hyperbolic definition, so this is e to the power minus 1 minus e divided by 2i, right? Because sin z equal to e to the power iz minus e to the power minus iz divided by 2i, right? So what is that? If you calculate that, this is I times e minus e inverse divided by 2. Okay, so sin I, the mod of sin I is equal to mod of this guy, so e minus e inverse divided by 2, and this is strictly bigger than 1. So yeah, so we have the statement is false. Okay, so let A be a finite abelian group of order 2025, then for every subgroup we have A is isomorphic. Okay, I have a space here. So let A equal to the cyclic group Z2025. Okay, so 2025 equal to, so let us do the prime factorization. Let me think. Yeah, so 2025 has a prime factor 3, so this 3 to the power 4 times, yeah, 5 times 5 square, so 3 to the power 4 times 5 square, yeah, this is the prime factor. So now we have what? So we have a subgroup H which has order, so we have a subgroup such that H is isomorphic to Z5 because 5 divides 2025, so this has a subgroup of order 5, right? So this is a finite abelian group, yeah. So if Z 2025 is isomorphic to, let's say, Z5 cross A mod Z5, right? Then what will be the order, or what will be the order of A mod Z5? The order is mod A divided by 5, which is 2025 divided by 5. This is 405. Okay, 405. So now okay, so if this will happen, then yeah, so if this will happen, then yeah, this is our conclusion. So the point here is that this 405 is again divisible by 5. Okay, so now Z2025 has an element inside that which has order 2025. Okay, but the point is, if you pick any element from the right hand side element looks like B comma C, and if you raise to the power 405, you will get B to the power 405 comma C to the power 405, and C to the power 405 is 1 because right hand side has order 405, so right hand side will be 0, and left hand side B to the power 405, as 5 divides 405 and this is Z5, so 0 comma 0. So that will imply, so the point is that if we have an isomorphism, then A maps to, let's say, B comma C, then A to the power 405 A to the power 405, let's say this map is phi, so phi of A to the power 405 has to be 0 comma 0, and if phi is an isomorphism, then A to the power 405 has to be 0, but this is not possible, right, because order of A is 2025, so this is also not true. Okay, so consider the map RT to RT given by LF equal to 3F plus 2F prime. Okay, so RT to RT L, this is linear transformation defined by 3F plus 2F prime, so LF equal to 3F plus 2F prime. What are they asking? So they are saying representative derivative, so then L is injective but not surjective. Okay, so let's say 3F plus 2F prime is 0. Okay, then what we have is that 3F equal to minus 2F prime. Okay, So the point is that if you choose a polynomial, so let's say f of t equal to a n t to the power n plus dot 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 a naught. Okay, so then f prime of t will be n a n t to the power n minus 1 plus dot 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 a1, right? If you can write it as a1t plus a naught. So then 3f plus 2f prime equal to 3an. So the leading term is non-zero. So 3n t to the power n plus lower term, lower degree. But the point is, as an is non-zero, this will be non-zero, right? So if 3f plus 2f prime is 0, that will imply that an is 0. So the leading term will be 0. Leading coefficient is 0. That means f is 0. You can do it by solving this differential equation also. It will give a solution inside exponential space, but RT is a collection of polynomials only. Okay, so you have to show the surjectiveness, right? Okay, now this is a linear transformation. So the point is, so let us restrict the linear transformation. So you can choose, so let us denote this space RT. So this K means polynomials with degree less than or equal to k. So this is perfectly mapping this RTK to RTK, right? Because if you choose an element from RTK, polynomial with degree less than or equal to k, then 3f plus 2f prime is also, right, pointing this. Okay, now we showed this L is injective, right? We showed that L is injective. Yeah, L can be viewed as a linear transformation from all polynomials degree less than or equal to k to the same space. Yeah, this is a well-defined linear transformation, and we showed that L is injective. So this has dimension k plus 1, and also the space has dimension k plus 1, and we showed that L is injective, right? So as L is injective, so what can you say? That by rank nullarity theorem, that image space, dimension of V, that is k plus 1, is dimension of the kernel, which is 0, plus dimension of the image. So we don't know the dimension of the image, the dimension of image of L. So dimension of image of L has to be k plus 1. Okay, so the image is, let's say this is, let us define this LK. LK is defined by this. So LK has also, so image of LK is exactly equal to RTK. Okay, so that means this is surjective. So if you choose any polynomial, any polynomial f, okay, so that lands inside exactly one RTN for some n, right? And then there exists a pre-image, right? There is a pre-image by this map. So what do you have? The function is surjective, so they are saying not surjective, so this is also false. Okay, so let sigma 1 to sigma 8t be elements of permutation group S236 such that sigma I cube is the identity permutation for each I. Then there exists I strictly less than j between 1 and 80 such that sigma I is conjugate to sigma j. Okay, all right. Sigma 1, sigma 2, dot sigma 8t such that sigma I cubed equal to identity in S236. Am I right? S236? Yes, S236 So so let us sigma be a permutation. So we know every permutation has a cycle decomposition, right? And so on. So they are disjoint cycle. So if sigma cube is 1, that means this is sigma I cubed, b1 up to bj cubed, and so on. That is identity, means each one of them has to be identity. Okay. So the length of the cycles, are either 1 or 3, because each of them has to be. So if a cycle, so if its cube is 1, then the length of the cycle, so j has to be 1 or j has to be 3, right? Because 3 is a prime number. All right. So now okay, so let us track the maximum length. So sigma can be written as, so if sigma cube is 1, then sigma can be written as product of 3 cycles, and so on, right? Product of 3 cycles. So I want to count that how many cycles are there, how many 3 cycles possible in a sigma. So this is 236, and you have to divide it by 3, then you will get the maximum number of cycles allowed here, right? You can say about this. So so greatest integer, so of 236 divided by 3 is 78, right? It is 78. So that means sigma has 79 possibilities, I mean length. Okay, let us do it here. Sigma has maximum cycle length. Sigma has maximum cycle length 78. Okay. Yeah. Right. Yeah, sigma has maximum cycle length 78, and you have to add sigma to be identity is the most specific case, so you only get 79, right? 78 plus 1, this plus 1 is for no cycles, no 3 cycles, just identity. That's it. Okay, now what you have is that okay, now yeah, now we know that let's say sigma and sigma prime are both product of 3 cycles of same number. Same number means same length. I mean, if sigma is a product of L3 cycles, and let's say sigma prime is product of again L3 cycles, then sigma and sigma prime is conjugate. This is a very famous theorem. This is standard in standard in any group theoretic book, so you can check it out. So then what you have is that let's say sigma 1 sigma 2 up to sigma 80. Let's let all our product 3 cycles, okay, and let's say any two sigma j and sigma I and sigma j, I not equal to 2, has distinct number of 3 cycle product representation, right? Then but we have only 79 choice. I mean there are only maximum we can multiply 79 number of 3 cycles, okay, but there are 80 elements. Then by pigeonhole principle we have at least two for I not equal to j has to be of the form sigma is a product of, let's say, L3 cycles, and also sigma j is a product of L3 cycles, okay. Then what you have by this theorem, then sigma I and sigma j are conjugate, okay. Okay, so this is true, okay. Okay, so for a permutation sigma belongs to extends if fix be the donate the set of fixed points of this, then the average is equal, okay. So let us do it here. So we know Burnside lemma, right? So this lemma is very important. So we know Burnside lemma. So let's say a group acts on a set X, then we have the number of orbits. So let's say in this action, so let's say G acts on X, right? So then we have a we have a relation between the number of orbits and the sum over all the fixed point, okay. So this lemma is very important. This is any standard, this is in any standard book of group theory. So let's say G acts on X, then the number of orbits, the total number of distinct orbits, the Burnside lemma says is that 1 by G summation G belongs to G fixed point of G, okay. Now to use this see this problem is very straightforward. If you know Burnside lemma, you can just do it quickly, right? So let's say S10 acts on the set 1 2 10, okay, to 1 2 10. So that this action, what is the number of orbit? Number of orbit is 1. Why? Because if you choose any element, if you choose any two element, let's say I am choosing I and J, okay, then there exists a permutation then there exists a sigma S10 which sends I to J, namely I comma J, this cycle sends I to J and J to I, okay. Yeah, clear? So that means this action has orbit 1. So that means this is 1. And what is 1 by mod of G? Mod of S10 is 10 factorial. So 1 by 10 factorial summation sigma belongs to S10 fix of sigma, this is 1. So this thing has a very probabilistic interpretation, so I will not go into that, okay. So this is true, okay. The set X such that X B comma C belongs to R square such that the polynomial has distinct roots in C is connected, okay. So what's the polynomial? X square minus bx, x square plus bx plus c, okay. So x square plus bx plus c, what are the roots of this polynomial? This is minus b plus minus root over b square minus 4c divided by 2. So if b square equal to 4c, then it will have same root. Okay, so b square equal to 4c, so point is b comma c, that is b comma b squared by 4. So that means y equal to x square by 4. This is the curve. Okay, y equal to x square by 4, right? Yeah, y equal to x square by 4. So if you draw the curve y equal to x square by 4, how can it look like? How can it look like? See, it's a parabola, right? It's a parabola. So y equal to x square by 4 is like that. Sorry. Yeah, y equal to x square by 4 is like that. So we are looking at r squared minus this set, right? We are looking at r square minus this set. So this will make the space disconnected, because if you choose a point from that and if you choose a point from that, you cannot connect these 2 points, right? And other way you can say this will make the space this space will not remain a path connected, but again this line b square, this parabola divides r square plane into 2 regions, right? This will be not connected. Okay, okay, so let us move on to the next problem. Okay, I have to check that I have done all the problems. 1 2 3. Yeah. 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 Okay. Yeah. The point interpretation will imply that the space is not path connected, but you can just directly do by definition, because x is connected, you know that the definition, x is connected if they are not separated by 2 open non-empty open sets, right? If it cannot be written as u union v, where u intersection v is phi and u and v are both open. Okay, so here take this as your first open set, and here take this as your second open set. Okay, yeah, so yeah, this is space will not be connected, this space will not be connected, because you can write it as union of this and this. Okay, so this will not be connected. Okay, so we will have, this is false, sorry, is false. We showed that this is not connected. So the integer from 1 to the power 6n, okay, 2 to the power 6n dot 2025 to the power 6n is divisible by 7. Okay, so we know that n to the power 7 is congruent to n mod 7, right? And n to the power 6 is congruent to 1 mod 7 if 7 does not divide n. Okay, now 2025 divided by 7, right? So we have to sum it up until 2025. Yeah, so 125 7 is just look at the greatest integer of that. This is 289, right? 289. So then up to 2025, how many elements are there, how many natural numbers are there which is divisible by 2025? That is 289. Okay, now now if n to the power 6 is congruent to 1 mod 7, then n to the power 6k is also congruent to 1 mod 7. Okay, now 1 to the power 6n plus 2 to the power 6n plus dot 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 2025 power 6n. So it is congruent to this is congruent to so let us say that a1 a2 dot 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 a289, these are all the factors of 7. So 1 to the power 6n is congruent to 1, 2 to the power 6n is congruent to 1 dot 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 1 plus, so yeah, so we can drop, so the point is we can drop the we can drop the factors of 7. So how many factors of 7 are there? So that means we have 2025 minus 289 mod 7. Is that clear? Right? Is that clear? Because we have 225 number. So whenever I have a multiple of 7, we can just say that is 0 mod 7, right? We have to drop this. So we have, so and otherwise, so the point is that b to the power 6n is congruent to 1 mod 7 if 7 does not divide b, and congruent to 0 if 7 divides b, right? So that is why we have this. So now this is what 2025 minus 289, right? 2025 minus 289 is 1736 mod 7, and this is nothing but, this is divisible by 7. Okay, this is 0 mod 7. So this thing is divisible by 7 for all n greater than equal to 10. Okay, so this is true. Okay, so thanks for watching. So see you on next video.